The kinetic theory of gases is a model that explains the behavior of gases based on the motion of their constituent particles, like molecules or atoms. It's a powerful tool that helps us understand the macroscopic properties of gases, such as pressure, temperature, and volume. Key assumptions of the kinetic theory of gases. 1. Gases are composed of tiny particles, molecules, or atoms that are in constant random motion. 2. The volume of the gas particles themselves is negligible compared to the total volume of the gas. 3. There are no attractive or repulsive forces between the gas particles, except during collisions. 4. Collisions between gas particles and the container walls are perfectly elastic, meaning kinetic energy is conserved. And 5. The average kinetic energy of the gas particles is directly proportional to the absolute temperature of the gas. The ideal gas equation is a mathematical expression that relates the pressure, volume, temperature, and number of moles of an ideal gas. It is derived from the kinetic theory of gases and is given by PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, R is the ideal gas constant, 8.31 joules per mole per Kelvin, and T is the absolute temperature of the gas in Kelvin. Examples of the kinetic theory of gases in action. Inflating a balloon. When you blow air into a balloon, you are increasing the number of gas molecules inside it. This increases the pressure, causing the balloon to expand. Boiling water. As water is heated, the kinetic energy of its molecules increases. Eventually, the molecules have enough energy to overcome the intermolecular forces holding them together in the liquid state, and they transition into the gas phase, steam, diffusion of perfume. When you open a bottle of perfume, the fragrance spreads throughout the room. This is because the perfume molecules are in constant motion and collide with air molecules, causing them to diffuse. The kinetic theory of gases provides a good approximation for the behavior of real gases under many conditions. However, it has some limitations. Real gases are not ideal. Real gases have intermolecular forces and their molecules do have volume, which can affect their behavior at high pressures and low temperatures. The kinetic theory does not account for the internal energy of molecules. It only considers the translational kinetic energy of the molecules. Despite these limitations, the kinetic theory of gases is a fundamental concept in thermodynamics and provides a valuable framework for understanding the behavior of gases. Would you like to explore a specific aspect of the kinetic theory of gases or the ideal gas equation in more detail?